The infinity puzzle. Well, this is the story of the 50 years' work that led to all of the current excitement about the Higgs boson, whatever that may be. But it's a talk really about the sociology and history of science rather than the technical details. And to show you why this needs to be understood much better, as of July, I'm sure we have now at last discovered this amazing piece of the universe. So much excitement has been generated that Time magazine, they have each year their selection of the person of the year, and one of the candidates this year is the Higgs boson. I promise you I am not making this up. And if you go to the web, you will find the nomination for it, and here it is, and I have removed everything that is wrong. And now I will reveal what it says. Take a moment to thank this little particle for all the work it does, because without it, you'd be just inchoate energy without so much as a bit of mass. As we will see, that is totally untrue. Most of our mass is locked in the atomic nucleus and has nothing at all to do with this. What's more, the same would be true for the entire universe. Having to be modest, we understand at most 4% of what makes up the universe, because dark matter and dark energy, we haven't got a clue what that is. It was in the 1960s that Scottish physicist, Peter Higgs comes from England, first posited the existence of a particle that causes energy to make the jump to matter. But it was not until last summer that a team of researchers at Europe's Large Hadron Collider, Rolf Hoyer, Joseph Incandela and Fabiola Gianotti, not to mention 6,000 others, and Rolf Hoyer, who is the DG, I think is almost the only experimentalist in Europe who is not a member of Atlas or CMS, at last sealed the deal, and in so doing, finally fully confirmed Einstein's general theory of relativity. And so it goes on. Okay. When you give talks to a general audience, one of the questions is, what is it they want to know? At what level do you want to give it? What is the real thing if you followed nothing for an hour? What is the single message that I would want you to take away? And to answer that, I thought, let's imagine what the universe would be like if there wasn't any of this Higgs stuff. There would be mass. It's locked up in the atomic nucleus. There would be no structure. And that's the message I want to give. The structure in the universe, the existence of atoms, molecules, maybe biology and life, is something that arises because of this business. And that's really what I want you to take away from here. But to show you what would happen if there wasn't any Higgs at all, this is what the universe, I think, would be like. Quarks, the seeds of neutrons and protons, would be still locked together to make these objects, and the mass of the proton and neutron is driven mostly by the kinetic energy of those quarks trapped inside that little volume. So even without the Higgs, even if the quarks had no mass at all, they would still be locked there. The neutron would exist, the proton would also exist, and because it's got electric charge, would presumably have an extra amount of energy or mass because of that. So the proton would be heavier than the neutron. The electron would have no mass, so there would be no chemistry. The size of a hydrogen atom is in part driven by the fact that the electron has the mass it does. If it was heavier, the atom would be smaller. If it was lighter, the atom would be bigger. If the electron had no mass at all, the atom would be infinitely big, which is the same as saying it wouldn't exist. The proton, being heavier than the neutron, would decay by beta decay, and it would decay quickly, because conventional beta decay, as we now know, is driven by the action of something called a W boson, which is very massive. It's the mass of that which causes the beta decay to be quite feeble. But in this world with no mass, that W would have no mass. And so the beta decay would happen very quickly. So there would be a universe, but not the one that we inhabit. So I'm going to say this has all got to do with structure. It answers the question, why is there structure in the universe? And in summary, as I've already hinted, the mass of the electron gives size to atoms. The mass of the quark, this is more subtle, but the particle physicists at least will perhaps follow the basic idea. The neutrons and protons that make the atomic nucleus feel a very short-range force. That's why the nucleus is very tight and compact. And that force, we have believed since the 1930s, is due to the role of a thing called a pion, which is a particle that transmits that force in the nucleus. The pion has a mass. In a world where the quarks had no mass, the theory would be what's called chirally symmetric, and the pion would have no mass. And so the nuclear force would be infinite range. The real world, because of Higgs, the quarks have a mass. That spoils chiral symmetry, gives the pion a mass, and makes the nuclear force short range. If you didn't follow that, it doesn't matter. The bottom line is the mass of the electron gives atoms a size, the mass of the quarks makes the nucleus compact. So that is really where the role of this thing begins to show itself in structure. So let's go back to the time before July, before we knew that these things were possibly correct. I was speaking at a literary festival, and for the first time in my life, rather than giving a talk like this, I was interviewing somebody, Peter Higgs, on the stage. And this was quite a nerve-wracking experience, but because the audience was really not a scientific audience at all, I decided to introduce some general ideas. And so I gave them an instant history, and this is what happened. I said, in 1964, Peter Higgs, and as we shall see, several other people, were scribbling equations on a piece of paper. As a result of that, today, this has led to a 27-kilometre ring of magnets underneath the French and Swiss countryside, which smash protons together, and the results of this are detected in detectors that are the size of battleships. They give wonderful images which tell things to scientists, or you can put it on the wall as a piece of abstract art if you like. And this is a measure of the size of the enterprise. This is not one of the collaborations. This is just those members of the collaboration that turned up for one of the meetings. So this gives you an idea of the vastness of what's going on. And the total price to date is of the order of 10 billion euros. And that's all as a result, I said, of Peter Higgs writing these equations. And I then turned to Peter and said, so if you today found a mistake in those equations, would you tell anybody? Well, we now know that there probably weren't any mistakes in those equations. But the next slide I showed was this one, which is Geiger and Rutherford in their laboratory 100 years ago, at the time that the discovery of the nuclear atom first happened. And you may think that I'm showing this slide to compare and contrast with the situation today, where, as we saw, you have got thousands of people working on this huge experiment compared with 2 or 3 people working on an experiment in a laboratory on a benchtop. That is actually not what I really wanted to bring out. It's this which is what surprised me. That is what the state of the world was in 1912, 100 years ago. Higgs and people came up with their ideas in 1964. The amount of time from Higgs and people to today is almost the same as Higgs and people to the discovery of the nuclear atom. That is what shocked me. It really brought home the vast time span that has been involved in discovering the nuclear atom, the ideas that we now believe give rise to the structure of that thing, and the experiments which are at last approving them. That, I think, was the shock. So, to give you some idea of what this is all about, I wanted to focus on 2 of the fundamental forces of nature, the electromagnetic and the weak, though this one illustrates all of them. I just show you this because 3 weeks ago I was in the South Pacific watching the total solar eclipse, and I haven't totally recovered from jet lag, so if I fall asleep in my own talk, please let me know. So electromagnetic and weak forces, and you can illustrate those by this picture of the sun. This picture actually is of the transit of Venus, which took place earlier this year, and it's nothing at all to do with my talk, but it's another example of sometimes you see something which completely shocks you. And it's this. Somebody pointed out that the size of Venus is about the same as the size of the Earth. So if you imagine that black blob there being the Earth compared to the size of the sun, and then when you realize that it's even in the foreground, so it appears even bigger than it is, it shows you how vast the sun really is. Anyway, that's apropos of nothing at all. So the sun is radiating light, electromagnetic radiation, that's what we see with, and in quantum theory that is carried by a little bundle called the photon, which has got no mass. The heart of the sun is where hydrogen is being turned into helium by a series of reactions, the first stage of which is controlled by this other force, the weak force. It is empirically weak because the agent The analog of the photon is this W boson. And whereas the photon has no mass, the W boson has a lot of mass. That is what makes the force feeble and causes the change from proton to neutron to take place quite slowly. And that is the reason why we are here, that the sun is only just managing to stay alight. It's been burning for 5 billion years so far, which has given enough time for evolution to happen. And it's about halfway through this cycle. So a way of giving an illustration is if you imagine yourself as a proton in the sun 5 billion years ago, by today there is still only a 50-50 chance that you have bumped into another one and set this process going. It's because that force is so weak that the sun has managed to burn this long. It is weak because we now know the W boson has a mass which is due to this Higgs business. So you could even say that the fact that life exists has indirectly come about as a result of all of this stuff. So it is something which is very relevant to us. It's not just an arcane thing for particle physicists to wonder about. So to give the background to this, let me just say something about the electromagnetic force and the infinity puzzle and where Higgs and co come in. So Maxwell created the theory of classical electromagnetism in the 19th century. In the 20th century, Paul Dirac added the other two great theories, namely Einstein's theory of relativity and the quantum theory, to Maxwell's theory to create the modern relativistic quantum field theory of electromagnetism called quantum electrodynamics. And with that, you can calculate properties of atoms, and in some cases to an accuracy of 1 part in a trillion, which, to give you an idea of what that means, it's like saying I could measure the width of the Atlantic Ocean to the accuracy of the width of a human hair. So that shows you how successful quantum electrodynamics actually is. Or it is that successful today. When it was first created in the 1930s, the moment you tried to calculate anything beyond the lowest approximation, you found infinity as the answer. Now, if you get an infinity as the answer to a calculation, you know that something is wrong. There's something basically flawed somewhere, and this is what I call the infinity puzzle. And the solution was found in 1947 by various people, including Julian Schwinger, who we will meet in a few minutes in this talk. And it's called renormalization. You don't need to know what that is, except I want to tell you one feature of being able to do this trick of getting rid of the infinity to reveal the real numbers behind the scenes, the ones that work to 1 part in a trillion. One essential ingredient of being able to do this was the fact that the photon, the agent of the quantum electrodynamics of the electromagnetic force, has no mass. That was a critical feature to be able to do this. Today, we have a theory of the electromagnetic and the weak force combined in what's called the electroweak force. And the problem, of course, there was that the W boson, the analog of the photon, has a mass. And so if you calculated with this theory, you would get infinity. And because the W boson has a mass, you would not apparently be able to get rid of it. And that was a problem that was around in the 60s, and it wasn't really solved until the 70s. And it's the solution of that which is going to be part of the story today. But the original theory was due to these 4 gentlemen here, Weinberg and Glashow at the top, Salam at the bottom right, and Ward, his collaborator, next to him. And, of course, you know that 4 is larger than 3, and 3 is the maximum number of people that can share a Nobel Award, which creates an interesting story in its own right, which we shall have to assess as we go along. The solution to how to do this was finally found by Toft and Veltman, who showed that if you started with that theory and did some tricks, which I shall tell you about in a minute, you could get rid of the infinities there and reveal the real numbers in both electromagnetic and weak forces, and that is where we are today. You can calculate with wonderful precision thanks to what they did, and they justifiably shared the Nobel Prize in 1999 for that. So what is it that they did, and what has it got to do with my talk today? And that's really what I want to set up. What they did was to show that if you started off with a theory which had got no mass, everything's fine, and if you introduce the mass by a clever trick, and that's the trick due to Peter Higgs and these 5 other people, collectively known as the Gang of 6, that if you use that trick, then you could solve the infinity puzzle. So the first message is, what these 6 people did has already been used to lead to a Nobel Prize for 't Hooft and Veltman. These 4 people, who ended up, 3 of them in the Nobel seats, we will see that that reduction from 4 to 3 was in part due to the fact that they also, or some of them, also made use of the work of the Gang of 6. So the thrust of my talk is going to be, the Gang of 6's ideas already have led to 2 separate Nobel Prizes. It's about time they were recognized for this, even independent of the discovery of this object in July, in my opinion. But let's move on. So I will just, before going on and giving you the answers, say this. The Economist, when they reviewed the infinity puzzle, said the Nobel Committee would be well advised to read Mr. Close's book before making their decision. Well, it's not that thick a book, so I hope that they're still reading it, because the decision has yet to be made. And although I didn't give any recommendations in the book as to where I felt the Nobel Prize should go, I will do today. But I will make it clear, I'm not making a statement today as to whether the prize should go to the experimentalists or the theorists or how it should be shared like that. That is not the issue I want to address. I want to address a statement that you see a lot in the media, which is, as 6 people all discovered the Higgs boson, and only 3 at most can share a prize, this will be a problem for the Nobel Committee. In my opinion, that is completely untrue, because actually some of the things that I told you were untrue. 6 people did not discover the Higgs boson, and what they did discover we will see, and I think it is today quite possible to identify which 3 out of those 6 come out in front in the race. So to do that, we will have to look at 3 separate things. First of all, to understand how did 4 become 3, what did the Gang of 6 actually do, and then how does 6 become 3, and why is it those are the 3 faces that I show at the bottom: Englert, Higgs and Kibble. So that's where we will get to. So how did 4 become 3? Well, to do this, it's really the story of the electromagnetic and weak forces unified. But let's first of all say some things about the electromagnetic force. Things that we know or maybe have forgotten or don't know. The electromagnetic wave that you're seeing me with is electric and magnetic fields that are oscillating in space, transverse the direction that the light travels. In particular, there is no longitudinal compression mode in a light wave. The light has a constant intensity, if you like. And in quantum theory, it is asserted in lectures, and it is almost correct, but as we will see, not necessarily so, that because of this theory having a property which is called gauge symmetry, it doesn't matter what that is, the photon, the carrier, has no mass. That is what the textbooks have all said. And I will straight away show you why there's this little caution. The proof that you could get rid of the infinity puzzle for quantum electrodynamics was presented in 1947 by Dyson, Feynman, Tominaga, and Schwinger. And an essential part of that, as I said, was that the photon had no mass. Now, Schwinger, however, was getting worried because he realized that he had been able to prove the connection between this fundamental gauge symmetry on the one hand and the masslessness of the photon on the other hand only in perturbation theory. He had not been able to find a completely general proof. And he was beginning to suspect that there wasn't a completely general proof. The reason why he was obsessed by this was the fact that he was at that stage beginning to have the first idea that it might be possible to build a theory uniting the electromagnetic force and the weak force. It was Schwinger who suggested there would be this W boson for weak, analogous to the photon here. And his insight was that if the W boson had a lot of mass, that would make the force appear very feeble. So that was the idea in Schwinger's head. But he was already aware of the problem, that if he made this theory with a massive W, he would not be able to solve the infinity puzzle. That is why he was worrying about, is it really true that gauge symmetry and masslessness go together? But he couldn't prove it at that stage. Then he inherited a student, Shelley Glashow, in 1961. And Glashow said to me that he remembers when he started that Schwinger told me to think about unifying weak and electromagnetic forces, so I did. For 2 years, I thought about it. And that's as far as he got initially. Meanwhile, according to John Ward, in 1957, John Ward wrote to Abdus Salam. The discovery of parity violation, which in the jargon eventually settled down to showing that weak forces had got vector and axial components, and vector is what the electromagnetic is. According to Ward, he wrote a letter to Abdus Salam to suggest that it might be possible to build a unified theory and they should work on this together. I should say there is no record of that letter anywhere that I've found, so the only statement one has to support that is Ward's statement, be it as it may. He and Salam did start working together, and by 1961 produced their first paper uniting these two ideas. In the technical jargon, it's a U3 model. There is no Z boson, there is no weak mixing angle. 3 years later, they finally got it right in their paper, which had all of the modern ingredients. It had a Z boson, it had a weak mixing angle, its structure was SU2 cross U1. So by 1964, Salam and Ward have indeed found the right answer to unite things. And here, incidentally, are the manuscripts that I got from Abdus's widow, Louise Johnson. And I just show it because it shows how things have changed today compared with back then. It's possible for a historian to go and look at this and see things crossed out and compare, with the final published version, and you learn things about the thought process. For example, you see on the left they had an abstract. They were obviously planning to send it to some regular journal rather than to Physics Letters, which is where it ended up. I just wonder, historians 40 years' time from today, going back and we do everything on LaTeX and it's lost on the internet somewhere, whether it will be possible to reconstruct the thought processes that led to discoveries. But, okay, that's just a side issue. But as we shall see, manuscripts tell an interesting tale, and I'm going to show you a manuscript later of Weinberg's paper that he won the Nobel Prize for, which tells a very interesting tale about the Higgs business. But anyway, at the moment, there are Salam and Ward in 1964 having found the right theory. Unfortunately, Glashow had found the very same thing 3 years before. Glashow in 61 had found the SU2 cross U1 way of doing it and published it. So Salam and Ward have replicated Glashow, but 3 years too late. They are unaware, as everybody was, of the possibility of using this trick that the Gang of Six come up with for two reasons. One, the Gang of Six have not yet come up with that until actually a few months later. Salam and Ward's paper was received at the journal on September the 24th. Guralnik, Hagen and Kibble, that are three members of the Gang of Six, their paper was received on October the 12th. The irony is, however, that those three people were working in the same physics department as Salam and Ward, and they obviously never talked to each other. In fact, it even gets worse than that, because here's a little side story of how to miss a Nobel Prize. Jerry Guralnik, one of those three, recalls what happened. In those days, Jerry Guralnik was a young postdoc, and he had been putting together the basic ideas of how to create mass in a theory, but hadn't yet got it all sorted out. So early in the spring of 1964, before any of all this stuff of Higgs and Broughton-Ongler and everybody else was finalized, Guralnik had got almost the whole thing completed, but not quite. And he recalls going and having a lunch with John Ward. Now, John Ward was, by that stage, a very senior scientist. He was the Ward of the Ward identities. He'd got a tremendous track record. Guralnik is a very young postdoc. So you can imagine yourself in that situation. You try to make conversation with this very senior, august character, who, I should also say, was quite, I'm not sure whether paranoid is too strong a word, but he was a very unusual person. Anyway, so Guralnik starts to tell a conversation. He says, oh, I've been doing this work on how to get mass into a theory. And Ward says, stop. Have you published this? And Guralnik says, no. Have you talked about it anywhere? And Guralnik says, no. Then he says, say no more. You must never discuss with people your unpublished ideas because they will steal them from you and take them for themselves. So Guralnik stopped. And as he said, at that moment I didn't feel that it was right for me to ask Ward what he was working on. Now, if they had spoken together, Guralnik would have learnt that there is this SU2 cross U1 idea that his ideas could be grafted onto. And Ward would have realised that here was an idea of how to put mass into the theory through the back door, but that's not what happened. Let's come to that. Yes, they introduced it by hand in 1964. We'll come to it, what happened later. Okay. So how did 4 become 3? That is the state we've got to at this moment. I think we've established why Glashow was there. He was the first person to publish SU2 cross U1. Salam and Weinberg, they are there because of work that the Gang of 6 did, which I shall now come to the second part. What actually is it that the Gang of 6 did? Well, how 4 became 3 is really the question of how 2 became 1, and what the Gang of 6 did. I shall now give... This audience is somewhat mixed. Anybody who has done electromagnetic theory as an undergraduate will be aware of the fact that when an electromagnetic wave hits a plasma, what happens next depends upon whether it's a low-frequency wave or a high-frequency wave. Those who have never done that, or don't even know what I'm talking about, may be aware of another phenomenon, or at least if they're the age of myself and some people in the audience, you may remember that when we were kids, you used to get fun listening on the long wave of the radio to radio stations from North America, because the ionosphere above our head is a plasma, and when a long wave radio signal hit that plasma, it's reflected back. So in a plasma, long wave or low frequency get rejected. But you can still see the stars through the ionosphere, which means that high-frequency electromagnetic radiation gets through. So that's just the thing to take for this little pedagogic example I'm going to give you in a moment, which is the way that electromagnetic waves behave when they hit a plasma. High-frequency get in, low-frequency do not. This is the question that Phil Anderson, condensed matter theorist, started thinking about in 1962. Remember, Schwinger was worried about whether there is a connection between gauge invariance and zero mass and couldn't prove it in general. And Anderson here is now going to give a pedagogic example that shows you can have gauge invariance and apparently have mass as well. The surprise is that Anderson didn't take the final step. But I'm going to show you this because I think that what is wonderful is that Anderson in this 62 paper has a pedagogic example of what this mechanism really is about. Forget all of this stuff that you see on the internet about politicians walking through crowds of people in a party and causing all this to give the Higgs mechanism an idea. This one here by Anderson is genuine, and as we'll see, I think it has everything. So imagine this electromagnetic wave hitting a plasma. If it's low frequency, it gets rejected. If it's high frequency, it gets in. And Anderson then thought, what would it be like if you were a creature that lived inside a plasma? What you would be aware of is electromagnetic waves only above a certain frequency. Now, frequency, by quantum theory, relates to energy. And energy with a minimum frequency that gets into the plasma is the same as saying a minimum energy gets into the plasma. A quantum with a minimum energy must have a mass, because the minimum energy is mc squared, and anything below that is forbidden. So a creature inside the plasma would only see electromagnetic waves carried by photons above a certain energy, and the creature would interpret it as being because the photon has a mass. That is what the creature would think. Now, that is only half the story, because a massless photon, as we said at the start, only has oscillations, the electric and magnetic fields transverse the direction of motion. There is no compression wave. Whereas a genuinely massive one would have all three. So how does that feature appear to the creature inside the plasma? Well, the answer is this, that the electromagnetic waves that get into the plasma, they set up an oscillation in the plasma itself in the longitudinal direction. So Anderson's pedagogic model has all of the features for a creature that lives inside a plasma of a gauge-invariant electromagnetic theory with massive carriers. There's one further feature, which is that the plasma itself can be excited, and this is known as causing plasmons, which is the analog of the Higgs boson, because to take this pedagogy example and apply it to the universe at large, all you need to know is that the vacuum that we live in is not empty, and suppose that it is filled with, let's call it an electroweak plasma. What that is, I haven't got a clue. In fact, that's what we're now trying to find out. But imagine that we actually are creatures living inside this weird plasma. And when W bosons propagate through it, below a certain frequency, they never enter. That is why we interpret them as having a mass. And you can test the idea by exciting this electroweak plasma to create a Higgs boson, which I've called a Higgson. And that we have now managed to do experimentally. So this pedagogic example, which has got all the features except one, was due to Phil Anderson in 1962. So why is it then we hear about Brout, Englert, Higgs, and all these other people in 1964? The answer is what Anderson was doing was completely valid for the situation he was interested in, namely a plasma sitting there, if you like, at rest, a well-defined frame of reference. If you try to apply that to the whole of the universe, what you're doing is reinventing the ether, which was done away with over 100 years ago. And so to make a relativistic analog of that is what we say in the trade, not trivial. That indeed is what Brout, Englert, Higgs, and these others first showed 2 years later, was how to make an ether which is so clever it hides itself from all experiments. It's a relativistically invariant analog of that. So to give a little bit, I'll just take 5 minutes out. This is one of those things that if you know what I'm talking about, you don't need me to tell you. If you don't know what I'm talking about, you're not going to get it from this. But it's on the slide, so I'll do it anyway. But it has some relevance for various things. So the idea that the photon has zero mass is actually very profound. If you took a random particle and asked what's its mass, it could be anything at all. If you find that its mass is 0.00000, you say there must be a reason for that. And there are profound reasons in quantum field theory which say there is a symmetry at work, and that the name for that is gauge symmetry. That is what everybody believed. But this was the fundamental question, really, that Schwinger was worried about, and which Anderson, in his example, has already given the example. Is it possible to have the symmetry at work, and yet the effects hide it? In this particular case, can you have gauge symmetry in the theory, and yet the carrier of the force appear with a mass? Can you hide symmetry? The answer is yes. And so you don't get scared. It's much more common than you think. So I'm just showing you this if ever you have to give a pedagogic talk. Take the classic example of gravity. The law of gravity is that particles attract each other in proportion to the inverse square of the distance apart, but it doesn't care what the direction is. It's three-dimensionally symmetric. So the fundamental law of gravitational attraction is three-dimensionally symmetric. And here you have a beautiful example of something which shows you that symmetry, a spherically symmetric galaxy. The sun is pretty well spherically symmetric because of that fundamental law. It exhibits the symmetry manifestly. This beautiful three-dimensional galaxy manifests the symmetry precisely. This one doesn't. This spiral galaxy, if the only thing you knew about gravity was this spiral galaxy, you would think that the law of gravity acts in a plane. Whereas we know that the real law of gravity is three-dimensional. So this is an example of hidden symmetry. The fundamental law respects all three dimensions. The actual structure that we see only operates in two. Why is that? What's going on? Well, in this case, you can see what the key is. Imagine that a three-dimensional galaxy like the one that we saw a moment ago. Imagine what happens millions and millions of years in the future. All those stars are collapsing inwards on each other due to the gravitational attraction. The chance that they are all in just the right spot, that they end up contracting to a point to make some massive black hole, it just don't happen like that. You know, they're going to be slightly off-center, and so two will go like that and then start coming back again. What is happening is that the more stable situation is this plane. So what you are seeing here has the key ingredient for it all, really. You've got a fundamental symmetry at work, but nature has more stable solutions that hide the symmetry. You are giving up the symmetry in order to gain stability. This also has a further example, because I've cheated you. There is more than one spiral galaxy in the universe, and here's just some of them. If you took pictures of all of the spiral galaxies, you would find they fill every which way in the 3 dimensions. So, over the whole of the universe, the 3-dimensional symmetry is there overall, or globally. But on a case-by-case basis, it is hidden because of stability. And this idea has been around since the days of the philosophers, 400 years ago. The philosopher Buridan worried about this highly symmetric case of a perfectly symmetric donkey, exactly midway between 2 identical bunches of carrots. And the philosopher argued that the symmetry of the situation meant it is impossible for the donkey to choose the ones on the right or the ones on the left, and therefore it will starve to death. And we know in practice that will not happen. But exactly why it will not happen is the sort of things that philosophers... Are there any philosophers in the talk here? We're all natural philosophers. Okay, good. So in reality, some small amount of asymmetry will make the donkey choose these and stay alive, or maybe choose those and stay alive. If you did this with hundreds and hundreds of symmetric donkeys, half of them would go to the left and half of them would go to the right, preserving the symmetry overall. But on a case-by-case basis, it's a life and death decision. This little idea is what, in physics, was taken over by Nambu and Jeffrey Goldstone in 1961. And this is the only real bit of physics in the talk, just to show you. Phi, along this axis, if you like, is the amount of stuff filling space, some sort of field that he's imagined. If there wasn't any at all, then the energy of the vacuum, let's define it as 0. And then Goldstone is considering the case, when I start adding this stuff, instead of the energy going up straight away, what happens if it goes down to a minimum, and then as I add more, it goes up? So this is a perfect example of what we just saw a moment ago with the carrots, that there is a stable solution this side or a stable solution that side. Well, in fact, it's more complicated, because in reality, you've got to, in Goldstone's picture, you've got the whole rotational as well. I'm not going to go through the maths of this in field theory, but again, this has an easy-to-see physical analog, which is, imagine a ball sitting on top of the base of a wine bottle, being here in Italy. As you look at it from above, it's completely rotationally symmetric, but of course it's highly unstable, and the slightest disturbance will make that ball roll down into the bottom and end up somewhere, so that on a case-by-case basis, what a moment ago was completely rotationally symmetric is now broken. The ball is here, or there, or there. Do it thousands of times, and the full rotational symmetry will be preserved on the average, but on a case-by-case basis, it is hidden. Now, often people in a general talk will say, well, but this is a bit of a cheat, because in principle, you could imagine the ball staying there forever. It's just because you haven't put it carefully enough that it will roll down. No, in principle, you can't. That you could imagine having a ball made of perfectly spherical molecules on top of this base, which is also perfectly spherical, and having the two things lined up so perfectly they will stay forever. Except room temperature means that these things are jiggling around, and so they will not stay there. To which the person will say, okay, but suppose I did it at absolute 0, where there isn't any jiggling. Then the quantum gets you. The fundamental axiom of quantum is you cannot both know precisely where a thing is without knowing what it is doing in motion. So there's a fundamental, very profound thing which says, even in principle, it is not possible for this situation to survive. The asymmetry must happen. Now, the problem with this is that, Goldstone and Nambu applied these ideas, but the desire to try and apply it to the case of the particle physics, in particular to understanding the nature of the W boson, is that electric charge in the theory means that these solutions, where the ball ends up around the bottom, in the real quantum field theory analog, will correspond to a wave going around with zero energy, because all of those solutions have got the same energy. So you can imagine rotating from one to the other. And in quantum field theory, that is like a massless particle in that mode. And a massless particle carrying electric charge when you try to apply it in this particular context. And the bottom line is there are no massless electrically charged particles in nature. So this is a very interesting idea which had applications in various areas of science, but apparently could not be applied to the particular one in question. Except that that is what Braut-Englert, Higgs, Guralnick, Hagen and Kibble, and also two young Russian guys whose names never get mentioned, discovered independently. That when you add a long-range field like a massless photon or a massless W in the theory to this particular idea, this rotational mode, which a moment ago you didn't want, turns out to be that missing third degree of freedom. This is the relativistic analog of the plasma longitudinal mode of Anderson. So from this, even if you haven't followed it, now let me just tell you what it does with regards to who gets credits. The first people to discover that you could make this relativistic analog of Anderson's work using these ideas of Goldstone were Braut and Englert. They were the first to publish the mass mechanism. It should be called the mass mechanism, not the Higgs mechanism, because as we see, Braut and Englert came in first. Peter Higgs published a month later, but what Peter Higgs uniquely did was drew attention to another feature of this theory, namely that there will exist a massive particle, which carries his name today, and it's the properties of that particle that experimentalists can study, which will reveal if the theory is what nature uses or whether it's just some clever idea that mathematical physicists have dreamed up. So Higgs uniquely, as we shall see, identified this critical feature, the boson that carries his name. Well, what is that in an instance, and why didn't the other guys say it? That model that I was showing you of the ball on the top, the mathematical analog of it, again representing it here, the ball drops into the base, and we were talking about what happens when it rolls around the bottom there, the angular mode, and that is the one that Goldstone didn't want, but we now know is the thing that gives rise to the third degree of freedom. But there's another degree of freedom, the ball wobbling up and down at the base of the valley. And in quantum field theory, that radial degree of freedom corresponds to a massive boson with energy, because energy is involved in that motion. And that is the boson that Higgs drew attention to, that carries his name. And it's actually not his 1964 paper that is interesting here, it is his paper in 1966, where he wrote down the Lagrangian for the massive boson to decay into two vector bosons in the jargon. There was for the first time the statement that the decay of this massive boson will have an amplitude proportional to the mass of anything that it gives mass to. And that is really the key feature that is being tested in the experiments at the LHC at the moment. Do the decays of this massive boson, are they in proportion to the masses of the things that they give masses to? Higgs drew attention to that in 1966, uniquely. Except, I discovered in Goldstone's 1961 paper, if you go down underneath that figure, you will see that he says infinitesimal oscillations around one of these minima, namely the bottom there, obey the equation, and that's an equation for a massive particle. This is actually the equation of motion of what we now call the Higgs boson, already in Goldstone's 1961 paper. Now, when I was writing the book, I wanted to get things correct, so I sent an email to Jeffrey Goldstone and said, am I right in saying that the Higgs boson is actually no different than your massive boson in your Nuovo Cimento paper? And I got this surprising reply, your question puzzles me, I'll have to think about it. Now, he's had 49 years to think about it. Anyway, so I left it there, and a year later, I was getting to the stage where the book was being completed and I needed to send in the final proofs. So I contacted Jeffrey Goldstone again and said, are you still thinking about it? And he got an instant reply and said, "Do not say I am still thinking about it. I think you are correct." And then he said, "However, I want it to be clear, that was not the one that interested me. I was only interested in this mode." So here was Goldstone sort of taking any credit at all for this away and so forth. But it's fascinating that it is in his paper. So although I'm not going to be including Goldstone's name in my Nobel Prize list, that's simply because I'm being asked to choose 3 out of the 6 of the gang of 6. The role of Goldstone in all this, I think, has not been given credit yet. And he, to my mind, would be a very serious contender for, if not this prize, for a prize. So the boson is the thing that we're really interested in as we move into the last part of the talk. Here is the chronological order of things. Brout and Engler published in Physics of Letters on the 26th of June, Peter's paper on the 31st of August, Guralnick, Hagen and Kibble in October. I asked Brout and Engler why they didn't mention what we now call the Higgs boson, and they said because they thought it was obvious. Peter Higgs, to his credit, said to me, yes, it was obvious, but he mentioned it. In Guralnick, Hagen and Kibble's paper, there is an equation of motion for something analogous to that, but it is a massless particle, which they don't want and they ignore it anyway. So of these, only Peter Higgs drew attention to a massive boson, and 2 years later drew attention to the fact that its decay could be used to test the theory. Interesting that having published the paper, Walter Gilbert wrote Peter Higgs and said, "Thank you for sending me preprints of your 2 papers. Unfortunately, I believe your conclusions are wrong." The reason for me showing that from Wally Gilbert has some relevance. If people want to ask me afterwards, they can, but not for now. So, how do 6 become 3? Well, sadly, Brout died earlier this year, and so Engler is the sole survivor of the people who first published the relativistic analogue of Anderson's mechanism. Peter Higgs is the only one that drew attention to the massive boson that carries his name, whose experimental properties are the things that can determine whether this is real physics or not, and I think that's why it's so critical. Finally, I've got Tom Kibble's face there, and I now need to explain why him. Well, I'll give you the answer why, and then see how this links also to the how did John Ward get missing out. So the 3 candidates: Engler, first to publish the mass mechanism, the first surviving one to do so; Higgs, the massive boson that proves the theory; Tom Kibble. It was 1967, 3 years later, when Kibble created what the real world is. All of this stuff done so far is rather idealistic. It is showing in principle how you can give a mass to the W boson, let us say. It doesn't discuss how the photon manages to stay massless. It was Tom Kibble who showed how it was possible to construct a complete theory where the photon remains massless and the W and Z bosons gain a mass. So Kibble actually, in his 67 paper, really made contact with the real world as we now know it. That's why I single him out for the 3rd. And also, as we will now see, because he played a role in at least 2 other people getting a Nobel Prize. And that will be Salam and Weinberg. So the question of how did 4 become 3 is explained by what Tom Kibble did, and it will in part now answer the question that you asked earlier about did Ward and Salam put the mass in by hand or what have you. And it's Weinberg in 1967 that starts this part of the story and shows a lot of interesting things, as we will see. Weinberg in 1967 came up with, completely independent, the idea of creating this SU2 cross U1 model, but critically, he was also aware of this mechanism because Tom Kibble had published his paper, and Weinberg realized that that was the key to starting with a theory and then ending up with massive W's and Z's and massless photons. So Weinberg incorporated and was inspired in part by Kibble. Weinberg mentioned this at the Solvay conference at the end of somebody else's talk, and then said, this raises a question I can't answer. Are such models renormalizable? In other words, can you get rid of the infinity? And Engler, who was still quite a young guy at this stage, stood up and said the answer to Weinberg's question is that yes, you can. He was actually wrong. Well, sorry, he was right, but he was not for these reasons. He and Brout had showed that the theory was finite, but not that it was renormalizable. It took another 4 years and a Tofton development to do that. But the point of showing you this is the following. That Weinberg had taken to the conference with him a manuscript of his yet-to-be-published paper. This is a paper that has been cited 7,000 times, by the way. And in it, you can now see why manuscripts carry messages. He had written at reference 3 his reference to Peter Higgs's work because he had talked with Peter Higgs earlier that summer and was completely aware of the history there. But he obviously at that stage was not aware of Broughton, Onglair, Guralnick, Hagen and co. Onglair has now made this remark after the talk, which has made Weinberg aware that there's these other things which are pointed out to him. So you see in the manuscript that he's got a little addendum underneath there. The arrow is put there by Weinberg to remind him when he goes back to Harvard to add that in. So Hagen et al., Broughton, Onglair are added in after the Higgs, and this is how then it appears in the journal. Higgs's name and references come first, Onglair and Broughton next, and people have taken that to think that Higgs's papers came first, but they did not. Broughton and Onglair came first, but they've been cited there second. That is part of the reason why Higgs's name has become so highly profiled, but it gets more exciting in a moment. That's 1967. That's physics letters 12. But you have asked an interesting question. Maybe you've read my book already, I don't know, but anyway, we'll see. Great. So this is the Gang of Six, correct references, correct order. Phys Rev letters 13, physics letters 12, Higgs. 4 years later, the Toft and Veltman proved the idea is renormalizable. Weinberg follows up with a paper to bring everything up to date. And in that paper, he has them in this order with those references. Let me just go back a second. Notice that Higgs's correct reference is physics letters 12, but it has become Phys Rev letters 12 and appears to be in the chronologically correct order. And indeed, that is the case. There is Weinberg's 71 paper, Higgs Phys Rev letters 12, Onglair Brout Phys Rev letters 13. This paper has also been cited thousands of times. And you can go through the literature and you can see this incorrect reference propagating like a Darwinian piece of, whatever it is, mutation, which also shows how people copy references rather than reading original papers. Lots of nervous laughter in the audience, okay? But this particular thing that's propagated through the literature and is part of the reason why people have associated it, or Higgs did it first. He didn't actually do it first. He uniquely identified the boson that experimentally confirms the idea, but he didn't actually do it first. But there is one further reference in Weinberg's paper there, which is completely correct and critical. See Tom Kibble, blah, 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 67. That is the paper that stimulated Weinberg to do this. That is the reason, in part, why I'm citing Kibble for my third choice. Yes, he did it in a complete generality, asking if I've got different mathematical group structures, and I can then siphon parts out. So the SU2 cross U1 is a particular example of that, but he was more general than that. So that is why I cite Kibble as the third of those, and it also helps answer the question of how the 4 became 3, as we will now quickly see. And Kibble explains that. So recap where we've come to as I just about come to the end. Glashow has come up with the SU2 cross U1 in 61. Weinberg in 67 has incorporated the ideas of the Gang of Six thanks to Kibble, and that's what singled him out. And then Toft and Veltman have then shown, using all these ideas, you create a renormalizable theory. So Salam and Ward, they missed out on the SU2 cross U1 because they were 3 years late. Salam in 68, however, also incorporated these ideas of the Gang of Six onto the work that he and Ward had done. And that is what distanced him from Ward, apparently, leading to what's been called the Weinberg-Salam model. But it still raises the question what happened to Ward, which now comes to the last interesting part of the talk, which is this. This is probably not visible, but it's perhaps not that necessary. There are 2 letters here, and the boxes are to show they've been written by the same hand, the P on the right and the P on the left, and so forth. What are these 2 letters? The letter on the left has been written to Bengt Edlund, who was, in 1971, the chair of the physics committee of the Nobel Foundation. My colleague and head of department has told me you are on the Nobel committee and that he has nominated another colleague of ours, Professor A. Salam. I know you'll detract from what a colleague writes, but truth must be told. Salam's greatest contribution is no doubt the modern theory of the neutrino, etc. So this is a nomination letter on behalf of Abdus Salam. And the other letter has been written by Abdus Salam, which therefore implies that the first letter was also written by him. So this is interesting for several reasons. Not that Salam was actually nominating himself for the Nobel Prize, so much as what he thought his primary work was. That he thought there on the left, Salam's greatest contribution is no doubt the modern theory of the neutrino, which is a completely separate story. And this letter is in the files at ICTP, and you can check this. So you will see that this letter was alive 1971-72. It wasn't until really everybody realized that what Toft and Veltman had done was so critical, and this phrase, the Weinberg-Salam model, came alive, that the switch from Salam's belief that his work on the neutrino was a critical thing to the belief that this unified theory stuff was a critical thing became noted. And the key that separates him and which changed the nature of the nomination late in the 70s was this. Weinberg had, in 1967, published his paper incorporating the mass mechanism into the SU2 cross U1 theory. Salam had also given lectures at Imperial College, independent of Weinberg's work, which incorporated the ideas of the Gang of Six into the SU2 cross U1, because Tom Kibble had tutored him. Tom Kibble was in his department. Tom Kibble had published the paper, and for the first time, and this is the question again that you asked, Tom Kibble had added mathematical group theory to the basic idea. If you look at Salam's CV, one of his great loves was group theory. And I think that although in 1964 this work had made no impact on him, in 1967, Kibble's tutorial, group theory, excited Abdus Salam, and he realized this was the missing link on the work with Ward. And Paul Matthews now sent a letter to Professor Waller, who was by then in 76 the chair of the foundation. I wish to confirm I attended the course of postgraduate lectures which Salam gave every term during the autumn term of 67, at which he described the unified theory of weak electromagnetic interactions, using the recent work of Kibble, done in our department, to produce spontaneous symmetry breaking in the context of his earlier work with Salam and Ward. Salam subsequently described this work at the Nobel Symposium. At the time these lectures were delivered, Weinberg's work had not appeared. Now, I know that some people have scurrilously said, well, of course, this is Paul Matthews' typed letter. How do we know that this was also not preceded by a handwritten letter? Well, whether it was or wasn't is not really relevant, because I've managed to check at least Bob Del Burgo in the department had a clear memory of being present at these things, and Chris Isham also has a memory which fitted in with the sort of timescales involved. And using Salam's diaries that Louise Johnson went through, we were able to put together when he was over here and when he was back at the Imperial during that time, and I think we've pinned down the dates pretty well to when these things took place. They weren't actually formal lectures, they were small-scale teach-ins with 5 or 6 people present in his office, which took place over 2 or 3 Tuesdays. And by complete coincidence, it seems they started, the first or second of these, was pretty well the very same day that Weinberg was over in the Solvay conference making his own suggestions. So that is what it was that separated Salam from Ward in the minds of the committee. So that's how 4 became 3. And we've seen that Kibble played the critical role here as well. And that is why I think that Kibble is the 3rd out of that first 6. So, in summary then, that is the Time nomination for the Person of the Year, and you now know why it has got very little relevance whatsoever to the physics of what this is all about. You have mass because of quarks are locked in the protons of the nucleus, not because of the Higgs mechanism. Peter Higgs isn't Scottish. There are more people than Rolf Hoyer et al., and it's got nothing whatsoever to do with general relativity, as far as I'm aware. So in summary then, this is what it does for us. The electron gives a size to atoms. The quark mass makes nuclei compact. The mass of the W is what slows down the weak interaction and lets the sun burn long enough for us to be here. It gives structure to things. We haven't answered all the questions. Why is it that the neutron is heavier than the proton? Which at the quark level is saying, why is the down quark heavier than the up quark? There is nothing at all in any of this that has a clue as to where that comes from. Why is the mass gap between those two big enough that the electron could be emitted in beta decay? No idea to that either. That's why I hope that there will be some unexpected feature in the data that will give us that critical clue. So that's where it is then. That we now know what this stuff does, and I've identified out of that 6 Onglair, Higgs and Kibble, and I would nominate them as my Nobel Persons of the Year 2013 for chemistry.
Okay. Thank you for the very interesting lecture. I think we are running a bit late, so if there, I will take, say, a couple of questions, if there are some.
Well, since you mentioned Goldstone, a few years ago they gave a Nobel Prize to Kobayashi and Maskawa, that certainly deserve it, and to Nambu.
Yeah.
And they forgot several other physicists.
Yes.
And I believe that Nambu should be coupled to Goldstone, and it's a nonsense instead to put Nambu with Kobayashi and Maskawa that in common have only the fact that they are of Japanese origin. And then
Sorry, I'm not saying this just because I'm in it. No, I'm not saying this just because I'm in Italy, but I found it quite astonishing that if Nobel Prizes were to be awarded, then Kabibo, Kobayashi and Maskawa should have shared that one. Everybody in physics knows of the CKM. And Goldstone and Nambu should have been linked together, certainly. I've no idea how that came about. Maybe that's another book. Yes. Unfortunately, they will not release any of their papers until long after we're gone.
These are more secret than secret service files. Okay. Well, if there is no other question, let's thank Frank again.